The paper we're diving into today is called Deep Forcing, training-free, long video generation with deep sync and participative compression.
And this one really tackles the Achilles heel of autoregressive video generation.
Right.
You take these amazing diffusion models that are trained on short clips, 5 seconds or so, and you ask them to generate a 1-minute video.
And they just fall apart.
They fail dramatically. You get this ugly buildup of errors. The motion slows down to a crawl, and the whole visual just collapses on itself.
So this solution, Deep Forcing, is pretty groundbreaking because it's entirely tuning-free.
Exactly. It's an inference-time trick. You take the existing self-forcing architecture, you don't retrain it, and you suddenly unlock over 12 times the extrapolation.
Going from 5 seconds to a full minute of stable, high-quality video, all from a frozen model.
Yeah, and it's achieving results that are as good as, or sometimes even better than, methods that do require a ton of expensive fine-tuning, like rolling forcing or long live.
And they do it with two main mechanisms. The first is what, deep sync?
Deep sync, yeah. That's all about stabilizing the global context. It dedicates almost half of the attention window to be a kind of persistent memory.
And the second part is participative compression, or PC.
Right. As the video gets longer, the model's memory, its cache, gets full of noise and junk. PC is a smart way to prune that cache.
So it keeps only the most important bits of history that are still, actively helping the model.
It throws out the rest. It's an incredibly clever and efficient path to temporal stability.
Okay, so let's unpack why this long horizon problem is such a big deal right now. It's not just about making longer, cooler videos for social media, is it?
Not at all, no. The whole field is sort of shifting from offline generation, where you just make one video and you're done, to these interactive systems.
You mean things like world models or autonomous agents?
Exactly. Anything that needs to generate frames in real time, one after another, in a continuous stream, that's all autoregressive.
And that's the core vulnerability, right? That autoregressive flow. Each new frame depends entirely on the last one.
It's the perfect recipe for error accumulation. It's like that game of telephone, but with pixels.
Yeah. Frame 10 has one tiny little artifact, a slight color shift maybe.
And frame 11 takes that as the absolute truth. Then frame 12 inherits both mistakes and makes it even worse.
And this isn't just a theoretical problem. You can really see the degradation.
Oh, you see it immediately. The visual quality just nosedives. Colors get weirdly oversaturated. Textures start to smear.
All the fine details just
evaporate.
They just vanish.
Yeah.
That's what they call temporal drift.
Now, people have tried to fix this before. I'm thinking of the LLM space with streaming LLM.
Right. That was a huge deal for text. They pioneered the attention sync idea, where you anchor the model to the first few tokens to keep it from losing context over long sequences.
But you can't just slap that onto a video model, can you?
It really falls apart. Video is so much more complex. It's 3D spatiotemporal, not just a 1D sequence of words.
So what happens when you try? Well, some of the earlier video work tried anchoring just the first 3 frames or so. And often the video quality would degrade anyway, or even worse, the motion would just stop.
Motion stagnation.
Yeah, the whole scene freezes because the model is too anchored to those static starting points.
You also mentioned the problem with the key value cache, the KV cache. For anyone listening, that's basically the model's short-term memory of past frames. Why does that fail?
2 big reasons: scale and policy. First, the cache just gets huge. A 60-second video has 12 times the frames of a 5-second training clip. That's a massive memory and computation hit.
And the policy.
The default policy is usually FIFO first in, first out. When the memory window is full, it just blindly throws out the oldest frames.
Regardless of whether they contain, the main character's face.
Exactly. It's a system that's just designed to forget critical information, especially when you push it way beyond its training wheels.
So the big question is, how do you stabilize context over hundreds of frames without killing the motion or just running out of VRAM? This brings us to deep sync, which, honestly, this part of the paper felt like a huge aha moment.
It really is. The common thinking, which we borrowed from LLMs, was that attention is all about the very beginning and the very recent past.
But that's not what they found when they actually looked inside the pre-trained self-forcing model.
Not at all. They found something fascinating. The model already had this strong, deep sync behavior built in.
What does that mean in practice?
It means that across all these different layers and attention heads, the model wasn't just paying attention to frame 1, it was consistently putting a lot of weight on frames deep in the middle of the sequence.
Interesting. So the model itself already knew that it needed these intermediate anchor points
Yeah,
to keep things coherent.
precisely. It was already trying to stabilize itself. We just weren't giving it the right tools.
Which is why the first part of their solution is just make the sink bigger, deeper.
Exactly. Their hypothesis was that these middle frames are essential checkpoints for things like subject identity and overall structure.
And the ablation studies back that up.
Dramatically. When they generated 50-second videos, they found that making the permanent sink size bigger up to, say, 40 or even 60% of the window.
Which is what, 10 to 15 frames?
About that, yeah. It led to huge jumps in their overall consistency scores and a big drop in aesthetic drift. It was clear proof that you need this extended, deep temporal anchor.
Okay, but locking down a huge chunk of early frames creates a new headache. What about rope E, the relative positional encoding? For anyone who needs a quick refresher, rope E is how the model knows how far apart two frames are in time. If you force frame 1 to suddenly look at frame 200, their positional codes are completely misaligned.
And that misalignment is just devastating for the output. It causes all these horrible visual artifacts, flickering, a massive drop in quality, and this thing they call rollback.
What's rollback?
It's when the generator just completely loses its mind and starts redrawing the old, clean frames from the sink, but in a corrupted, glitchy way. It's a really spectacular way to fail.
So the fix they came up with is super clever. They don't get rid of rope E, they just nudge it.
Yeah, they strategically offset it. They realized the problem was only on the time axis. The spatial relationships within a frame still need to be correct.
So they only adjust the temporal part of the rope E index.
That's it. They use a temporal offset sync.
So you're not telling the model frame 1 is now looking at frame 200, which is a huge, confusing jump. You're using the offset to say, hey, just treat frame 1 as if it's temporally close to the new frame.
You got it.
Yeah.
It realigns their relative positions and bridges that huge time gap. It's a very elegant fix that keeps the spatial stuff stable while anchoring the temporal context.
But it worked.
Perfectly. When they compared it to other sync methods, theirs was the only one that didn't have these progressive failures. No flickering, no rollback, just stable video.
So deep sync fixes the stability and the rope E problem. But like we said, even if the frames are stable, you still end up with this enormous, noisy KV cache after a minute of generation.
Right. Deep sync keeps the foundation strong, but it doesn't solve the memory bloat or what they call attention dilution.
Attention dilution.
Yeah, when you extrapolate that far past the training data, the cache is just full of redundant, noisy, kind of irrelevant tokens. The attention mechanism has to spread its focus across all that junk, and it gets diluted.
Which leads to that overall degeneration you see in really long videos.
Exactly. And since the old FIFO policy just throws away the oldest stuff, which might be the most important, you need a smarter way to manage the cache.
Enter the second pillar, Participative Compression, or PC.
And it's surgical. It's not a blunt instrument like FIFO. It only kicks in when the sliding window is completely full and only on the very first, most noisy diffusion time step.
Why just the first one?
It's the most efficient. The theory is if you can give the model the right context at that highest noise step, you set the trajectory for the entire rest of the denoising process for that new chunk of frames.
Okay, so let's get into the mechanics. How does it choose which tokens get to stay?
So first, it partitions the cache. You've got your sync tokens, S. They're sacred. They always stay.
Of course.
Then you have your recent tokens, R. They're also kept for local coherence. You don't compress those. Everything else, the history in the middle, becomes the candidate tokens, CANAD.
And those are the ones on the chopping block.
Right. And the decision comes down to an important score.
And what makes a token important?
It's all about participation. The score for any given candidate token is just the sum of all the attention it gets from the recent query tokens.
So it's asking, is the stuff I'm generating right now still paying attention to this piece of history?
That's a perfect way to put it. If the recent context is actively looking back at that token, it's deemed critical for understanding the long-range scene. You keep the top C tokens with the highest scores.
And your new compressed cache is this beautiful curated thing, sync, the top historical tokens and the recent ones.
Exactly. And the visualizations in the paper are so cool. They show that the tokens PC chooses to keep line up perfectly with the most important semantic parts of the image.
Like what?
Like the main body of a robot or the moving tentacles on an octopus. It proves the score is actually identifying contextually essential information.
Okay, let me play devil's advocate for a second.
Yeah.
If you're only keeping tokens based on recent attention, aren't you risking long-term amnesia? What if a really important detail from 30 seconds ago is just temporarily not being attended to? Couldn't it get thrown out by mistake?
That is a fantastic question, and it's why the system works as a whole. Deep Sync is your safety net. That handles the absolute long-term identity. It's the permanent anchor.
I see.
Participative compression is managing the intermediate history, the stuff between the sync and the immediate present. Because it's guided by the recent frames, it's making sure the history it keeps is the most relevant for the current action.
So Deep Sync holds the who and what, and PC holds the relevant how it got here.
That's a great way of thinking about it. And once it picks those top tokens, it does another quick ropey adjustment on them, a little top, just to make sure they slot in perfectly between the sync and recent tokens without any temporal gaps.
And there was a surprising finding here too, right? About using noisy queries for the scoring.
Yeah, this was really counterintuitive. They found they got the best results when they calculated the importance score using both the clean history and the noisy queries from the current denoising step.
Wait, using noisy input helps you select the best clean memory. How does that work?
It was a real shocker. It shows that even at maximum noise, those initial queries aren't just random static. They contain some kind of structural hint about the desired outcome.
So they're context aware, even when they look like noise.
Apparently so. Using that combined signal massively outperformed random selection. It suggests importance isn't just about what a token is, but how it relates to the dynamic process of creating the next thing.
All right, let's talk results, because this is where a training-free method going up against fully trained models gets really interesting.
It's where the rubber meets the road, and the results are genuinely surprising.
Looking at the V-bench long benchmarks for 30 and 60-second videos.
Deep forcing, with its frozen backbone, is either matching or straight up beating the trained models, like rolling forcing and long live. It has better overall consistency than long live, better aesthetic quality than rolling forcing.
That alone is a massive win for an inference time only method.
It absolutely is. But the metric that really jumped out at me was dynamic degree.
Yes, this measures how much motion is in the video.
And this might be the most important discovery. Deep forcing scores around 57 on this metric. The training-based methods, they're down in the 30s and 40s.
Which supports that theory we were talking about earlier.
It really does. It suggests that when you fine-tune a model so heavily for stability, you might be accidentally training out its ability to create natural dynamic motion.
You're punishing it for being creative, in a way.
Sort of, yeah. Deep forcing seems to preserve that raw dynamism because it isn't changing the model's weights. It's just giving it a better memory system to work with.
So you get more expressive dynamic videos that don't suffer from that motion stagnation problem. And it's not even slow, right?
Not at all. The throughput is basically identical to the baseline self-forcing, over 15 frames per second on an H100.
How is that possible? Isn't all this compression work an extra step?
It is, but that cost is completely offset because running the attention mechanism on a smaller, cleaner compressed cache is way faster than running it on a full bloated one.
That makes sense. And beyond the numbers, there's the user study. What did actual humans think?
This is the ultimate validation. Using a two-alternative forced choice setup, the preference for deep forcing was overwhelming.
In what areas?
Across the board, really, but especially in subject consistency. People preferred deep forcing's ability to maintain a coherent subject over 84%, and in some cases up to 96% of the time compared to baselines.
So even if some pixel-level metric might be slightly lower here or there, what people actually perceive as quality and coherence is significantly better.
That's what it comes down to.
So you have a method that's training-free, dynamic, fast, and people strongly prefer the results. The final check with the Gemini VLM just confirmed its stability was right up there with the best trained models.
It really establishes a new paradigm. Deep forcing proves that you can solve these massive challenges in long video generation, the error accumulation, the memory issues, the temporal drift, entirely at inference time.
It's just a much smarter way of using what the model already knows.
It's a fantastic argument for exploiting the capabilities that are already latent inside these huge pre-trained models. You don't always have to default to another expensive round of fine-tuning.
If you can just understand the model's inherent attention patterns, you can build smarter systems around them.
And that leads to a really interesting question, I think, for you, for anyone listening who's designing these systems. Given that deep forcing works on a totally frozen model, what is the true limit of context that's already hiding inside today's diffusion models?
Hmm.
We found these clever inference time tricks to push stability out to a minute, but what other optimizations could we find? Maybe in spatial attention or in the cross-attention layers? What could unlock multi-minute or, maybe even multi-hour generation with the architectures we already have today?